So I'm going to talk to you about characterization of the solid electrolyte interphase layer on the lithium-ion battery anode. So just a very quick overview. It's not a particularly long presentation. We'll talk a little bit about the samples, how they were prepared. We'll then look at some XPS using both the conventional aluminium K-alpha and the silver L-alpha source, and primarily drawing conclusions on the structure of that solid electrolyte interphase layer by the increased sampling depth. So that'll be some conclusions. So the samples were actually supplied to the APS lab in Japan by Dainen Material Company Limited, and they were commercially produced coin cell type lithium ion batteries. The solid electrolyte interphase is particularly of interest in these lithium ion batteries, as it provides the passivation layer of the anode, which prevents further electrolyte decomposition. And initially I thought the SEI layer was a bad thing, but it in fact isn't. It's absolutely vital in the performance of the lithium ion battery. And it really dictates the performance in the reversibility of charging and discharging. So it must be lithium ion conducting to allow lithium ions to transport towards the anode, but importantly electronically insulating, so that you're not getting sort of continuous reduction of the electrolyte. And the presence and stability of the SEI, as I've said, is fundamental. So these samples were the classic coin cell. They were disassembled, obviously in a glove box environment. The structure, it has this, I guess that's a sort of trade name for the electrode, the positive electrode. The electrolyte is lithium hexafluorophosphate with dimethyl carbonate as a solvent. The separator between the electrodes is cell guard, again, I guess another sort of trade name. So we essentially had access to 3 samples. The first was as manufactured, so it's undergone no charge or discharge, so it's freshly assembled. A sample that has undergone 1 cycle, and then another sample that has undergone 100 charge-discharge cycles. And as we're aware, these types of samples are very atmospheric sensitive. So the sample preparation was done in a very environmentally controlled glove box. Now that happened at Dainen's lab, and the samples were transported to Kratos using an inert sample transporter. So then that was, there was a sort of quite large physical distance between the 2 labs in Kyoto. I just included this slide as maybe a sort of precursor to what Simon might talk to you about tomorrow. This is one solution, the inert sample transporter. Again, it's just using the inert environment that the samples were prepared in the glove box. But we also have something that may be more useful in a sort of lab-based environment, moving from a glove box in the same site, which are these so-called shuttle sample holders. And they essentially have an evacuable volume here. So they're just evacuated this one-way valve using a little hand pump. And it's not a brilliant vacuum, but it does allow you to transfer from a glove box to the instrument, evacuate that, lift the lid off the sample holder, and then your samples can just be analysed under the UHV conditions. So this is a survey spectrum from aluminium excited survey spectrum from our 3 samples. Grey is the as manufactured, the sort of orangey colour is the single charge discharge, and blue is 100 charge discharge cycles. And we can see what we'd probably expect. I don't think there's any real surprises. The formation of the solid electrolyte interphase layer on the lithium-ion battery has occurred, and we can look at the sort of chemistry as that progresses through the charge-discharge cycle. So the quantification, again using the aluminium, shows that we've got an increase in the fluorine signal and the lithium, and a decrease in the carbon signal. So we can make sense of that by looking at the narrow region scans. We can see that there's some interesting sort of chemical shifts going on as we increase the number of charge-discharge cycles. Some nice sort of changes in particularly in the phosphorus region, the 2p region. These are mirrored also in the chemistry that we see in the lithium region. So what's happening is that we can see that from curve fitting our fluorine region, it's noted that the as manufactured sample here is already showing some degradation of the lithium hexafluoride phosphate component into this lithium with fluorine bonded. So we've already just by manufacturing got some degradation, and that SEI layer is beginning to form. After the first charge-discharge cycle, there's a peak which we assign to lithium fluoride, and again we're still seeing some of the electrolyte on the surface of the anode material. And as we go to the heavily cycled sample, we're seeing even more degradation product. So the electrolyte is degrading and forming this layer on top of the graphitic anode. If we look at the carbon region, again, we see a strong component from the graphitic carbon. And then as we increase the number of cycles, we see sort of organic type species in our carbon 1s spectra. And also we start to see this carbonate feature at the high binding energy. So that increases relatively as we increase the cycles. So this is just the quantification of the relative area of those components. So the graphite decreases. I guess we're attenuating the graphitic layer with our SEI layer, which is growing as a consequence of the cycles. If we plot the same data on a sort of bar chart, so here we're actually plotting the relative change relative to the graphitic carbon for the first cycle and the 100 cycle sample. So we can see the build-up of both the sort of organic degradation products and this carbonate layer. And if we look at the lithium components, they're increasing relative to our as produced sample. So both of these are positive, so significantly increasing the lithium fluoride. But the relative amount of the lithium fluoride in particular decreases with increasing cycle, and we get more of the lithium carbonate. So the literature suggests that the reduction of dimethyl chloride, so the solvent, dimethyl carbonate, results in generation of lithium methyl carbonate, lithium methoxide, carbon monoxide, and methane. So there's some very complex chemistry going on here, but this is kind of where we're assigning these chemistries. So colleagues then repeated the analysis with the silver excitation source, and much the same as Stuart pointed out, we can see that our signal to noise is not so good with the silver excitation source. We can obviously count for longer to improve that, but again, with such mobile light elements that we're analyzing, as well as the sort of fluoride materials, I think acquisition time was tried to keep to a minimum. So the changes or chemical shifts that were observed were sort of mirrored, very similar sort of changes in the chemical states as a function of charge and discharge. Again, if we look at the carbon 1s with a bit more detail, we can see a very strong graphitic asymmetric component. But again, there is already on the as produced sample, this is the as produced sample, there is some degradation product already associated with the anode material, increasing the charge discharge cycles. We see attenuation of the graphitic carbon anode, and an increase in the organic and carbonate species. Sorry, people waiting in the lobby. So we're seeing, let's scroll down. Yeah, so we're the biggest sort of observation there really is just again that attenuation of the graphitic signal. Even though we're sort of sampling deeper into the material, we're still looking at the same core level. So that has higher kinetic energy, greater sampling depth relative to the aluminium. We're still attenuating that graphitic carbon, implying that we must be generating a relatively sort of thick SEI layer. The difference is here that if we plot again the relative changes of those components relative to the non-cycled graphitic anode as prepared, we see increases in the carbon species, also in the carbonate. The real difference is that the lithium fluoride relative component increases. So we're seeing now an increase of the lithium fluoride and the carbonate with that greater sampling depth. In contrast to the aluminium, both those components are increasing. And that's allowed us to sort of conclude that because we're seeing this increase, we're looking deeper. This lithium fluoride layer must be sitting below the lithium carbonate in the SEI. So we are seeing a concentration gradient through the SEI layer. So this is just a sort of a schematic diagram where we've got a higher concentration of the carbonate species towards the surface of the material. The lithium fluoride degradation product, or what becomes the SEI layer, is much closer to the sort of graphitic carbon anode, and we're sort of estimating that the SEI layer is probably around about the same sampling depth as we would expect for the silver excited carbon 1s, which is about 19 nanometers. So in conclusion, the SEI layer has a greater lithium concentration closer to the anode, with the lithium carbonate, which is probably as a result of degradation products from the cathode migrating to the anode and reacting with the lithium to form a carbonate species. The SEI layer after the 100 cycles is about 20 nanometers thick. I think, as Stuart pointed out, that from an instrumental point of view, the HACSPES is relatively easy to use. The change between the two sources is all automated through the software. We now are able to quantify the results because we've got the traceable RSFs, and we're taking care of the transmission function. And using the HACSPES gives us a greater sampling depth, as Sarah pointed out, access to a greater number of core levels and good cross-section sensitivity, even for lighter elements, particularly if you compare it to the higher energy photon sources. Finally, just acknowledgments: Dainen for providing the sample, and Watanabe-san and Takashi-san from Applications Lab in Shimadzu for providing the data. So thank you very much.